motion of a particle is governed primarily by three equations. So if I want to calculate the equations or derive the equations, first we will consider the motion with constant velocity. Now we know that the velocity is defined as dx by dt, where x represents the change in position. So since velocity is constant, if I rearrange and make dx on the left hand side and integrate from x0, where this is the initial position, x is the final position, and at x0 the time is 0 and final position time is t. So I get this, and because velocity is constant, I take this out of the integration, velocity being constant, and I arrive that the displacement is equal to velocity into time, where v is constant. But if I have motion with variable velocity, that means constant acceleration, then first I will define acceleration, which is dv by dt, where v is the velocity, which means rate of change of velocity. So if I arrange, I can write down that dv is equal to a dt, and now I will integrate both sides. Because a constant, it can come out of the integration, and I will integrate with a limit u, which is the initial velocity, and v is the final velocity, u when time t equal to 0 and the final time is t. So if I integrate, I will get v is equal to u plus at. Velocity is final velocity, u is the initial velocity, acceleration a, and t is the time. So this is a very important equation of motion, v equal to u plus at. Now there's another equation where we are going to derive in this way, that dx dt is the velocity. So we calculate or we define the velocity as dx by dt, which x is the change in position. So now if I substitute the value of, in this v, if I substitute the value of dx dt, the equation looks like this. Now I will rearrange and integrate. So I will integrate in this way. The initial position is x0, final position is x. At that time t equal to 0 and the final time is t. So if I integrate, I get x minus x0 ut, u is the initial velocity, into time, half at square. So this x minus x0 is my displacement, and displacement is related as s or del x equal to ut plus half at square. U is the initial velocity, a is the acceleration. Like this, I have the third equation, which is v square is equal to u square plus 2ax del x. Del x means the displacement, or you can say s. How do I do it? If I can write in this way. I define the acceleration as dv dx into dx dt. And then I take acceleration v into dv dx, this definition, and then I rearrange in this way, that the velocity I integrate from lower limit as initial velocity u and the final velocity v, and the x dx I integrate the position from the lower limit starting initial position x0, final position x. So if I integrate, I get v square minus u square is equal to 2as or del x, which represents displacement. A is acceleration, u is the initial velocity, and v is the final velocity. So primarily we have three equations: v equal to u plus at, s is equal to ut plus half at square, and v square minus u square equal to 2s. Now from the third equation, s is equal to ut plus half at square, we can calculate the displacement of a particle in nth second. Just if you follow this, suppose a body moves from here till the final position in time n. So if I then just the previous second, I can say the displacement traveled is s in suffix n minus 1. So for this, if I use the equation s is equal to ut plus half at square, in place of t I will have n, and minus this will give me for the time n minus 1, because if I want to calculate the displacement for nth second, which means the displacement covered till the 10th second or till the nth second minus the displacement covered just before that second. So after doing some calculation, I arrive that displacement for the nth second or in nth second is equal to u plus a by 2 to n minus 1. N stands for the second which number second? Is it 10 second or 15 second? A is the acceleration, U is the initial velocity. Now, if we have motion with variable acceleration, then how do we calculate? We take the same definition of acceleration and velocity, and because acceleration is not constant, we write down in this fashion that my initial velocity is v1, final velocity is v2, and I integrate with v dv, and my, remember, this acceleration do not go outside the integration, and the final initial position x1 and x2, because I'm integrating as a function of position, so I have to consider the lower limit and the upper limit as the position x1 and x2. So these three equations, which were on the linear motion or straight line, but if we consider a particle moving under gravity, then how does the position graph look like? Say this particle or ball is thrown up, it reaches to the maximum height, and then because of gravity it comes down, and we have this position time graph. It reaches the maximum height and then it comes to the ground. So this is the position time graph when a ball is thrown up against gravity. So what will happen for the same motion if we plot the velocity time graph? In this case, the velocity, what happens? It increases. First, when it is thrown, the velocity is 20 meters per second. Then as it goes up high, because of the gravity, this velocity decreases and becomes zero at this point, at time t equal to second, when it reaches the maximum height. From there, the velocity is again increasing, but because it is increasing in the other reverse direction, so we plot the velocity in the negative y-axis with time. So if anyone asks that what will be the three equation of motion for this problem, for the motion under gravity, then we use the same equations that were discussed or derived earlier, but in place of acceleration, we will substitute the value of acceleration due to gravity. Now, based on these three equations of motion, we can do some problems. Let us say that you are driving a car and suddenly you notice a board where you have to control your speed, and your speed of the car now is traveling from 108 km per hour. Now you reduce it to 72 km per hour, and this reduced velocity came for traveling 100 meters at a constant acceleration. That means here the velocity is decreasing and it is retardation. That means negative acceleration. So you have to calculate the acceleration and how much time you have taken for this decrease in speed from 108 to 72. So first I will take the initial velocity or initial speed as 108 and convert in meter per second. Final velocity 72 km per hour, I convert to meter per second. And I use this third equation, v square is equal to u square plus 2s. S is the displacement, v and u is the final velocity and initial velocity. If I substitute, I get the acceleration or retardation or negative acceleration, which is 2.5 meter per second square. Then I use the first equation, v equal to u plus at, and substitute this value acceleration here and get the time, that by how much time this car has reduced its speed from 108 km per hour to 72 km per hour. We do another problem where this example, here you have that the acceleration is a function of time which is not constant, and it is given as acceleration is equal to 2t square. So now they are asking you that if it is at rest at the origin at time t equal to 0, find its position of that particle, velocity and acceleration at time t equal to 1 second. That means the particle at time t equal to 0 was at origin at rest. So you have to find out what is the particle velocity, position and acceleration when it is at time 1 second. So I already have a, it's variable, it's not constant, but it depends upon time. So a into, I will just substitute the value of t as 1 second, I get the value of acceleration at 1 second. Now I will use the velocity acceleration definition, dv dt is equal to acceleration. So dv dt is equal to acceleration, and in place of acceleration I will substitute 2t square, and then I will integrate dv on one side where in terms of velocity, where the initial velocity is 0 and the final velocity is v, initial time 0, final time t, and from here I will calculate the velocity in terms of time. And then I substitute at time t equal to 1 second, I get the velocity at t equal to 1 second, which is 2 by 3 meter per second. Similarly, I will use the definition of velocity as dx dt, rate of change of position, and dx dt is velocity, and I already have the velocity value as 2t cubed by 3, so I will substitute here. Now I will integrate in this way, taking x to the function of x to the left hand side and the time to the other side, and I will integrate with the limit 0 to x, where 0 is my starting position, x is the final position at time t equal to 0 and final time is t. So I get the displacement of position x is equal to t to the power of 4 by 6. So this is as a function of time. So if I substitute t equal to 1 second, I will get the position at t equal to 1 second as 1/6 meter. So we come to the end of this lecture.